Now we will continue the association analysis and look at the association rules. First, how to create, and then what kind of rules are we going to like, and are they good measure to indicate if a rule is interesting. To look at the definition, kind of definition for association rules, as we can see, if there are people are buying butter whenever they buy a diaper, so you can get a rule saying that diaper implies butter. So this type of association rules we can form given a market basket set of transaction database. So now a association rule, if X implies Y, means that X and Y are item sets, and generally we evaluate the rules based on two metrics, the support and confidence. These are the two original metrics with which people started studying the association rule, though there are some new metrics that have come in because of some observed limitations with these. But as we can see here, if you look at the milk and diaper leads to butter, then we look at the support count for milk, diaper, butter together and see that there are two transactions where they are occurring together out of 5 total transactions. So we see that it has a support of 0.4 or 40%. And for looking at the confidence, what we say is that among the transactions where milk and butter is diaper are happening, butter is also present in 2 out of 3, that is in 67% transactions. So we look at the count of the milk, diaper, butter together and then divide it with the count for the milk and diaper. So how do we reach the association rules? The two-step approach is, first we look at frequent item set because we want a good support, and then we generate the rules for which we have a high confidence. So if we have a frequent item set such as A, B, C, D here, then how many rules can be created? So the candidate rules are, in general, it is approximately 2 to the power of k. So if an item set has k items, it requires approximately 2 to the power of k minus, actually we subtract 2 because we can have one rule which is the entire set implies phi and null, and then null implies entire. These are redundant rules which are not going to give us any information because of the null. So for that reason, when we had 4 items in this item set, we have got 2 to the power of 4 minus 2, that is equal to 14 rules, which is a large number, and sometimes we have item sets which are much bigger than this. So we need to think in terms of how can we find interesting rules without studying each and every rule. So one approach we can take is comes from the a priori property. So when we are talking about confidence of A, B, C leading to D, it can be larger or smaller than A, B leading to D, because as we can see in both these cases, the denominator is different. In one case, you are looking at the support for AB, and in other case, support for A, B, C, D. And then the numerator is also different. One case ABD, and in the other case it is ABCD. But if you are generating the rules using all the terms, that is the difference. In this case, we generated a rule which did not have the term, one of these terms. But if we generate rules which have all these terms A, B, C, D, then what happens is that the confidence for ABC will be greater than confidence for AB implies CD. For the simple reason that numerator is same and the denominator in this case is support for ABC, and in this case support for AB, in this case support for A. what happens is that we know that from the a priori property that support for AB is always smaller than support for A. Similarly, support for ABC is always smaller than support for AB. So what that means is that denominator is reducing. So what that means is this is less than equal to, this is less than equal to, and the numerator is same. For that region, what we are getting is that confidence for this rule is greater than or equal to the confidence for this rule. So this property may help us in pruning some of the rules, thereby making the evaluation process faster. So if we create the lattice of rules starting with the same 4 items A, B, C, D, at the first level we say we can possibly have 4 rules which imply B, C, D implies A, A, C, D implies B, A, B, D implies C, A, B, C implies D. We start measuring the confidence for each one of them, and we find that this rule has a low confidence. So now we can draw conclusion that BCD implies A has low confidence. The BC implies AD will have a lower confidence for the simple reason that in this case the denominator comes from the support of BC, which is higher than the support of BCD. So once the denominator is higher, so what it means is that the confidence for this one is even lower. So in that sense, what happens is that there are several rules which can be pruned, and we can look at the interestingness from the remaining rules. And we can also use the a priori approach for creating the new rules. For example, if we have CD implies AB and BD implies AC, and then we can produce a new rule D implies ABC. But we can prune this if we realize that AD implies BC does not have the greater confidence, because if there is a rule AD implies BC, so then we know that this will also lead to this, and then the confidence for this rule will be lower than for this rule. So we can prune this rule based on the lower confidence for this rule. So essentially, because the D is subset of AD, so it is going to have a higher level of support. And now to look at the rule generation using the single minimum support. So that is when we had studied the frequent items and then tried to generate rules from this. We thought that given a one minimum support, that helps us generate the frequent item sets, and based on that further steps. But in real life, what happens is that we do not like to have the same level of support count for all the items. Consider a simple grocery store. They sell thousands of items, and if you look at, potentially it is possible that there are hundreds of customers come and buy milk there, but lesser number of people may come and possibly buy butter, and even lesser number of people come and buy honey. So here, but then they want to know, even for the other products for which there is not sufficient support, they want to know if there is any pattern with respect to the buying habits of those items. So for that reason, they do not like to have a uniform minimum support. And there are more regions that is generally the expensive products are sold less frequently than the inexpensive products. And as we know, the shop or the retail chain or whoever who is interested in studying the sales pattern have higher interest in finding about the movement of the goods which are expensive. It's possibly they give them a better profit margin. So for that reason, they would like to set a minimum support level there, and still they look at any interesting patterns emerging there. So now once they set differential support patterns, let's say the minimum support for milk is at 5%, for Coke is at 3%, then broccoli is at just 0.1%. Then what happens is, when you have created the larger item sets which combine the milk and broccoli, you need to look at a minimum support which is the lower of the two. So that means it is becoming 0.1%. So now the support is no longer having a monotonic, anti-monotonic property. So what it means is that milk and coke is infrequent, but milk, coke and broccoli is frequent, because even though the milk, coke, broccoli is superset of milk and coke, it is still maintaining the frequency because this minimum support used for both these cases is different. So in this case, the problem of finding the frequent item sets and deriving the rules is going to be more complex. And then when we are looking at the patterns evaluation and finding out the rules which are uninteresting and redundant and prune accordingly, so we may want to use some interestingness measures. Originally, the support and confidence were the measures to check the interestingness of a rule, but they may not be effective in all cases. So people started using the mode measures such as the lift, then J measure, etc., to look at if the rule is interesting. Now let's say we have a contingency table for the rule X implies Y. So how does it come? We look at the support for X and Y. So we are getting a support of F11. Then support for X when Y is not, then we are getting F10. Similarly, support for Y when X is not there, then F01. When both X and Y not there, so F00. So when we create this contingency table, we can analyze to see if there is an interesting pattern among them. So now let's look at the coffee and tea. We see that there are 20 people who take tea and 80 people who are not taking tea. And then there are 90 people who are taking coffee, and then there are 10 people who are not taking coffee. And there is a division of the people who take coffee and not take tea, so on and so forth, as per this table, contingency table. So now let's look at the association rule. Tea implies coffee. So now we look at the confidence. The probability of coffee when they are taking tea is coming to, there are 20 people who take tea and out of them 15 are taking coffee. So it is coming to 15 by 20. So the confidence is 0.75. So that looks pretty high. But then if you look at the people, number of people who are taking coffee among the total number of population, which is 90 by 100, so the probability of person taking a coffee is 0.9. So compared to this 0.9, actually 0.75 is low. So because of that, this rule is misleading. Rather, you want to have a rule which says that not tea implies coffee. When you analyze that rule, what you see is that the people who are not taking the tea, there are 80 people, and out of them the people taking coffee are 75. So that means it is 75 by 80, which is coming to 0.9375, which may be more interesting than, which has a more credibility compared to the other rule, which is tea implies coffee. And if you want to study the independence from purely statistical point, we may use these probability measures. Let's say we have a population of 1,000 students. Out of them, 600 students know how to swim and 700 students know how to bike, and then 420 students know both how to swim and how to bike. So now the probability of person knowing how to swim is equal to 0.6, and probability of a person knowing how to bike is equal to 0.7. And then probability of both S and knowing both is equal to 0.42, which is 420 by 1000. So what happens here is that we are seeing there is a statistical independence between the swimming and biking. So this is giving us a statistical measure because it is same. When you look at whole population, the people who can swim is 60%. So similarly, if you know the population who know both swimming and biking, there also when you're looking at the people who know the biking, there are 700 people. Among them again 60% of the people know how to swim. So their swimming has nothing to do with the bike, knowing how to bike. So this is, so you can get that in this case this is statistically independent. But if we get this probability to be higher than this product, we can say there is a positive correlation. And if it is less, we can say there is a negative correlation. So now this may help us solve the problem. We can define a new measure which is lift. So here we say that the probability of y given x, which is a conditional probability, divided by the probability of y, that can be used to check whether there is a good lift with respect to one of the rules. So the interestingness we can measure by the probability of x and y occurring together divided by the probability of x and probability of y. If it is greater than 1, we know that there is a statistical correlation. So now we take the same problem of people who have a liking for coffee and dislike, etc. So we are getting a, when we look at a confidence 0.75, but the probability of coffee is 0.9. So we are getting a lift which is 0.8333. So what this means is that there is a negative correlation between coffee and tea. So now this explains that this rule is not good. But even lift also has its own limitations. So if we are looking at a situation like this, this happens many times when we are studying the web and we are trying to identify whether there is any correlation between the terms. Suppose that we find 10 documents which have got both the words X and Y, and there are 90 documents that we have studied which have neither X or Y. So now we have got this contingency table, and then we have got another contingency table where X, there are 90 documents which have got X and Y, and there are 10 documents which have neither X nor Y. So now we want to find out which one has the higher lift. So we see that in this case we are getting a lift of 10, while in this case we are getting a lift of 1.11. So clearly this should have been more interesting, considering that majority of the documents are having both the terms X and Y. But then the lift measure is giving us a lower number here compared to this. So if we are looking at a statistical independence, then this is giving simply 1. So we are getting a, so the point is that these measures also have their own limitations. So we need to study further, and there is a significant interest in studying this topic to arrive at interesting association rules. So people suggest that there should be subjective elements included to evaluate. So the objective measures are based on simple computations which are statistical based. There are numerous measures of association that can be used. But the subjective measures come from the user's own interpretations. And the rule will become interesting if it contradicts the expectation of the user. Similarly, a rule becomes interesting if it is actionable by the user. So suppose, to look at the interestingness, it is generally associated with unexpectedness. Suppose based on a domain knowledge, you are expecting the frequency of some elements, and some elements are expected to be infrequent. But what the evidence gives you is that this is the kind of evidence that you are going to get. So then what you can see is that this term is representing, these elements are representing something which is high interest, essentially because this was, so here whatever you see, then what this evidence is showing is something which is along with the domain knowledge. And then if you see that something is infrequent when you expect it to be frequent, or it is frequent when you expect it to be infrequent, then it is clearly something which you want to study further, and that is something you have learned from the data.